Hi guys, for this video we'll be looking at physics revision for SPM. The paper is tomorrow. If you want to go through the other physics revision videos, I have another two. I'll leave the link in the description below. Kalau nak versi bahasa Melayu, saya akan tinggalkan pautan dia dalam huraian di bawah ya. Alright, so we're going to do a few topics based on my SPM analysis, based on the trial analysis. I have selected a few topics, alright. If you want to get the document for that, I'll leave the link in the description below as well. All right, so let's get started. So the moon takes, first let's look at gravitation. The moon takes 27.3 days to orbit the Earth. So what we have, we always write down first. This is the orbital period of the moon. So we have T moon, and this is 27.3 days. Okay, at what height should the geostationary satellite be? Now we've given the radius of the moon. So we have R moon, which is 3.83 times 10 to the power 8 meters. And then we also have the radius of the Earth. All right, so the question is, what is the height? We want to know the height of the moon. Now, a geostationary satellite, of course, is a satellite that is stationary geographically. That means if the satellite is just above above Malaysia, then it will always be above Malaysia. So for example, if this is the Earth, and let's say this is Malaysia, and the satellite is here, what will happen is the satellite will always remain here, even as the Earth is rotating along on its axis. So this doesn't mean the satellite is stationary, of course. The satellite is also moving together with the Earth, it's rotating. Now, that means the orbital period of this satellite around the Earth would be, so the period for the satellite would be 24 hours. So now what we have is, we have the orbital period, two orbital periods for the moon and for the satellite. Both are orbiting the same body. We are orbiting the Earth. So the moon is also orbiting the Earth. And then we have the radius of the moon, orbital radius of the moon. Orbital radius is from the center of the moon to the center of the Earth. So now what we can find is the orbital radius of the satellite. So when you have this question, when they give you two periods and one radius, or it could be the other way, it could be the other way around as well. They can give you two radii and one period, ask you to find the other. This is of course using Kepler's third law. So what formula do we use here? We use, this one will be given to you. So we are using the formula Ts square over R, okay, let me do that. T1 square over R1 cube is equals to T2 square over R2 cube. So this will be given to you. This is using Kepler's third law. Kepler's third law says that the square of the orbital period is directly proportional to the cube of the orbital radius of an object, right? So what we are going to do here is we are going to find, since they want the height of the moon, the height of the moon, or rather the height of the satellite, sorry, we want the height of the satellite. The height of the satellite is here, from here to here only, right? Let's call this h. However, what we get from this formula will be the radius, orbital radius of the satellite, not the moon. So now, if we use the formula, what we can do is we can put the radius on top. So radius of the satellite over the orbital period. This radius is cubed, and then the orbital period of the satellite square. This will be equals to radius of moon cube over orbital period of moon square. So we just have to substitute all the values in. So I'm straight away going to do this for you because this is revision. So the radius of the satellite will be, so now what we have to do is multiply this and then cube root the whole thing. So this will be this one cube. So I'm just going to substitute the values in directly. So this will be the radius of the moon cube, which is this, So this will be 3.83 times 10 to the power 8, the whole thing cube, and then multiplied by the period of the satellite square. So the period, you have to be careful to use the same units. So 24 hours, since this is days, I'm going to change this to 1 day. Note that you can change these to hours as well. It doesn't matter as long as both periods are the same units. As this goes to the radius as well, both must be the same unit. So this one multiplied by, if I just change to 1, then it's much easier. So 1 square, and then we divide this by period of the moon. Period of the moon, 27.3 days. So 27.3 square. And then the whole thing we need to cube root. So just use your calculator and you will get this value is 4.2243 times 10 to the power 7. Now, of course, we are not looking for the radius of the satellite. What we want is height. So what do we have to do? The radius of the satellite will be the height of the satellite plus the radius of the Earth. So we are going to subtract the radius of the Earth. So therefore, we are going to do the height of the satellite is the radius of the satellite minus the radius of the Earth. And so we just put in the value of 4.2243 times 10 to the power 7. And then we need to subtract this radius value is given to you, 6.37. You don't have to memorize the radius of the Earth, times 10 to the power 6. This constant is given to you. Okay, so now we will get our answer of 3.59 times 10 to the power 7 meters. Now, I advise you to pause every time and try first, and then after that, check your answers after I've gone through that, right? Okay, let's go to the next topic. So next topic that was asked a lot in these year's trials, again, this is not a prediction, this is just based on analysis. So a lot of the questions that came out were from nuclear physics. So let's look at this question. A radioactive sample J decays into K. So J decays into K with a half-life of 3 days. Let's write that down first. So we have T half is 3 days. Okay, its initial activity, 1,600 counts. So A naught is 1,600 per second. Okay. Now find the activity after 15 days, 15 days later. So how do we do this? So again, just pause and try yourself first, then you can check the answer. So 15 days later, we can use the formula. Okay. Initial activity. The activity after a certain number of time, or after a certain amount of time is initial activity multiplied into 1/2 to the power of n. Now n here represents the number of half-lives. N is the number of half-lives. So the first thing you need to do is find the number of half-lives, because what we have is the time that has passed is 15 days and the half-life is 3 days. So what's the number of half-lives? So very easy. This is also we can find with the formula. The number of half-lives is just the time passed divided by the half-life. That will give you the number of half-lives. So the time that is passed is 15 days over 3 days. So we get 5 half-lives. So now we can substitute it inside here. And so A will be equals to initial activity A naught is 1,600 multiplied into 1/2 to the power of 5. So this will be just 1,600 divided by 32. And so the answer is 50 counts per second. All right, let's look at B. Calculate the time taken for 93.75 of the sample to decay. Okay, this is very important because when we use the formula, so we can use a similar formula, but instead of activity, we use number of undecayed nuclei. So n naught 1/2 to the power of n. Now, again, this represents, both of this represents undecayed nuclei, nuclei that have not decayed. So if 93.75 has decayed, if we want to use the formula, first we need to find the number that has not decayed yet. So the number of undecayed nuclei N will actually be 100 minus 93. The percentage N will be 100 minus 93.75. And this is, of course, 6.25. So this is 6.25%. 6.25% has not decayed. Now we can substitute into this formula. So N is actually 6.25%. So divided by 100 of the original number of undecayed nuclei, right? 6.25% of the original. So multiplied into original number. So then we substitute this again on the left side. So you get 6.25 over 100 N naught is equals to N naught into 1 over 2 to the power of N. So you can see N naught will be eliminated here. And then now what you do here is 1 over 2 to the power of N equals to, use your calculator and get the fraction for this. Usually this works. You don't have to use logarithms here. You don't have to use log. You just use your calculator and get the fraction version. So the fraction version of this will be 1 over 16. And 1 over 16, of course, is 1 over 2 to the power of 4. And now you straight away know what the value of N is. So by comparison, therefore, N is equals to 4. Now, this is not the time taken, once again. This is the number of half-lives. So therefore, the time taken will be 4 half-lives. 4 times 3 days, as given by the question. So 12 days. So it takes 12 days for 93.75% to decay. Please remember, once again, this is for undecay. All right, next. So this is for nuclear energy, the second part, 6.2. The equation for decay of radium, so they've given you an equation for radium here, right, is this. So they gave you radium will decay into radon by releasing helium and energy. So given that the atomic mass is this, the atomic mass of radium is this, the atomic mass of radon is this, and the atomic mass of helium is this. So calculate the mass defect. So whenever we are doing calculations involving nuclear energy, we always find mass defect first. From the mass defect, then we use E is mc squared to find the energy that is released. So once again, I will advise you to try and pause and try the question first. Okay, calculate the mass defect. So how do we get the mass defect? The mass defect is the mass that is reduced. So the mass defect is how much mass has gone down, how much the mass has gone down. This mass that has gone down, that is missing, has actually been converted into energy. So we take the initial mass minus the mass of the products, because mass has been lost. So definitely we will have more mass at the beginning. So you have to take the mass of radium, which is 226.02536, this one here. And then we have to subtract the mass of radon and helium. So minus, please don't forget your bracket here. So radon will be 222.01753, and then helium as well, 4.00260. So when you subtract everything, you will find the mass defect is 0.00523 atomic mass units. Right. Now, once we've gotten that, then we can calculate the energy. So they want you to calculate the energy release, but this time in mega electron volts. Please do not forget this conversion. This will be given to you. So first, the formula that is involved, of course, is E is mc squared. So we have to substitute the mass in here. However, always remember when you're substituting, please check the units. The mass that you need to substitute into this formula is in kilograms, SI unit. So first we need to change this value in AMU into kilogram. And how do we do that? It will be given to you right here. 1 AMU is this many kilograms. So if you want to go from AMU to kilograms, we have to multiply by this value. So therefore, mass is 0.00523 multiplied into 1.66 times 10 to the power negative 27 kilograms. So this answer is in kilograms. And the answer that we will get here is 8.68 times 10 to the power negative 30 kilograms. Now we can take this value and substitute in here. So we will get E is equals to 8.68 times 10 to the power negative 30 times, this is the mass, and C squared. C, of course, is a constant. Speed of light in vacuum, 3 times 10 to the power 8, 3.00 times 10 to the power 8 squared. E is mc squared. And therefore, the energy that we will get here is 7.81 times 10 to the power negative 13 joules. Now, this is in joules. Joules is the SI unit. We are using all SI units here. Kilogram and meter per second. And so when we want to change to MeV, look at this conversion. We are going from joules back to MeV. So how to do that? Divide by this value. So therefore, this is equivalent, rather this is equals to 11.81 times 10 to the power negative 13 divided by 1.6 times 10 to the power negative 13 MeV. And so the value that we will get here is 4.88 MeV. So this is how we do calculation for nuclear energy. All right, the next topic is quantum physics. So quantum physics, we have all these constants given to you. So let's try the question based on that. Now, the electromagnetic waves of wavelength this are shown on the surface of metal with work function of this. So let's write down what we have first. We have the wavelength, which is 2.2 times 10 to the power negative 7 meters. And then we have the work function. So we have the W, which is 3.10 times 10 to the power negative 19 joules. So what they want you to calculate, the energy of a single photon. So energy of a photon, we are going to use the formula E is, energy is HF. However, we don't have frequency here. Whenever we don't have frequency, we substitute frequency with, please do not forget your wave formula. C is equals to F lambda. C is the speed of light or speed of all electromagnetic waves. So therefore, we can substitute F is C over lambda. We have lambda here. That's why we use HC over lambda instead. All right, so now we just have to substitute the values inside, excuse me. So H is given to you here. H is this, so we got HC, but don't use HC because this is in electron volts per nanometer, electron volts nanometer. We don't want this, we want H. So 6.63 times 10 to the power negative 34, Planck's constant. Here, negative 34 joules second. And then this one multiplied by C times 3.00 10 to the power 8 divided by lambda. So lambda here also given. This is 2.2 times 10 to the power negative 7. So here we don't have to use work function yet. And so this value here, the answer that we get here is 9.04 times 10 to the power negative 19 joules. So this is the energy of a single photon. So what is the maximum kinetic energy of the emitted photoelectrons? So once this light hits the surface of the metal, what is the energy maximum kinetic of photoelectrons? So now we can use Einstein's photoelectric theory formula. So we use energy of photon is equals to the work function plus maximum kinetic energy, Ke max. This is the energy of photon. So now we can use the values that we already found earlier. So we will use You want to find Ke max. Let's make this the subject. Kinetic energy, maximum kinetic energy will be the energy of the photon minus the work function of the metal. And so this we can use what we found earlier, 9.04 times 10 to the power negative 19, subtract 3.10 times 10 to the power negative 19. These are the two values that we found earlier. And the value that is given, sorry, work function is given. We found the energy of photon earlier. So we just substitute the work function here that's given to us. And so the maximum kinetic energy here is simply 5.94 times 10 to the power negative 19 joules. Okay, now the next question is find the maximum speed of the photoelectron. Once we have the kinetic energy, then we can find the speed simply by using formula for kinetic energy. So Ka is half mv squared. Now, v square will be 2Ke over m. And so we have 2 multiplied into the kinetic energy that we found earlier, 5.94 times 10 to the power negative 19 joules and divided by the mass of electrons. So mass of electrons is another constant that's provided for you, 9.11 times 10 to the power of negative 31. This is the mass of the electron. So 9.11 times 10 to the power of negative 31. V would just be the square root of this. So the answer that you would get is 1.14 times 10 to the power 6 meters per second. Right. So this is the formula for Einstein's photoelectric theory. Now we also have some other formulas here. That's the work function. So we have the work function is hf naught. F naught is the threshold frequency, right? Okay, so you can use this formula in various different ways. Now let's go on to the next topic, electromagnetism. This is another big topic that came out a lot for this year's trials. And so we're not going to fill this in. You should already know. This is your magnet holder, the C-shaped core. And then we have the permanent magnets here. And then we have the conductor, and then we have the galvanometer. All right, so now electromagnetic induction. Always remember induction right hand rule, Fleming's right hand rule. So what will happen to the motion of the copper if both are stationary? So electromagnetic induction can only happen when there is a cutting of the magnetic flux. So in this case, if both are stationary, nothing, the flux is not being cut, there is no deflection. The needle does not deflect. So what if we move left and right? So the magnetic field lines, the flux is here, north to south. This is the flux, right? So if you move this copper rod left and right, are we cutting any lines? No. When there is no cutting of lines, then there is no electromagnetic induction. So therefore, there is no current, there is no induced current, which means whether you move it left or right, there will be no deflection. Okay, what if we move the copper rod up? So if we move the copper rod up, then the force is in the upward direction. Yes, we are cutting the field now. So then we have to use our right hand. Use your right hand, determine the direction. So determine the direction of current in the rod first. So F is up, B, F is your thumb, B is the magnetic field direction. So according to our paper, it should be to the right. So the current end is going away from you, right? Your middle finger. The current is going away from you into the plane. So current is going into the plane. So it's going in here. So that means galvanometer will deflect here. The galvanometer deflects, according to our textbook, the galvanometer deflects where the current goes in. So it's going to deflect to the right. So this is right. Okay. Now, when we push the rod down and the magnet is stationary. So force is now down. So again, use your right hand. Force is down, B is to the right. Okay, the magnetic field direction is still to the right. Current should be coming towards you. So if current is coming towards you, current is coming out here. So therefore, current will be going into the galvanometer here and it will deflect to the left. So there's a deflection to the left. Now, what happens if the rod is stationary? So now what happens when we move the magnet up? When we move the magnet up, what happens is, it is as if we are applying a downward force on the copper rod, even though the rod is not moving, because this is relative motion. If the magnet moves up, relatively the rod is moving down. Please remember this, because there are experiments where you clamp the rod. So if you move the magnet, then the rod moves in the opposite direction, relative motion. So force is down. So again, you should get left as we just got, right? So if you move the magnet down, then it is as if you're applying an upward force on the rod. And so this one will be right again. So what if you move both together in the same direction at the same speed? Relative motion will be 0, right? Because there is no relative motion. They are not moving relative to one another, even though both are moving. So no deflection again. Okay, so this is electromagnetic induction. Now, what happens when you have a solenoid? So this is the permanent magnet, this is the galvanometer again, and this is the coil, the solenoid. So what happens if the motion is stationary and stationary? Once again, you need to be cutting the magnetic fields. The magnetic fields here, it's like this. Okay, so this is on the magnet, not to south, like that. Okay. Okay. So the magnetic field in the coil will only form later if there's a current. So now we want to cut. So if both are stationary, there's no cutting. There's no active cutting. Not just overlap. It needs to cut. So no. Now if you move the solenoid in towards the solenoid, okay, you move the solenoid, we move the solenoid towards the bar magnet. Sorry. So now we are moving the solenoid towards the bar magnet this way. Solenoid. Now we have to use Lenz's law. Lenz's law states that the direction of induced current will always be such that it opposes the change causing it. Please remember Lenz's law and Faraday's law. All right, please memorize them. So what happens? How to oppose this movement? So the opposition of this movement will be the magnet must push the coil back. How will the magnet push the coil back? This must be the south pole as well. So it's south and south, then it pushes the magnet. So this is opposing the motion of the magnet, the motion that's causing it. So if south is here, north is here, what rule do we use to find the direction of current? Right hand grip rule. Thumb is north. So we're going to point the thumb north and the current is going like this. So the current on the top is going into the plane on the top. All right, so it's going into the plane here, which means current is going up here and it's coming down here. It's going in here. Deflection is to the right. Okay, so what if we move the solenoid away? If we move the solenoid away, moving the solenoid in this direction, what will happen is the opposition will be to pull it back. The magnet will try to pull it back. So, or rather, the pole here will be such that it will try to pull back instead of go away. So in order to pull back, this must be north. So if use a right hand grip rule, if north is here, then the current at the top should be coming out of the plane towards you, right? So current is coming out here and going in here, which means deflection to the left. Okay, now what if the magnet is stationary and then we want to push, magnet is stationary and we want to, the solenoid is stationary and then we want to push the magnet. So if you push the magnet in to the solenoid, the opposing motion will be to push it back out. This is north, and so this will be north again. This will be north to push it out. So north, we know that it will be left, just like the example just now. If we are trying to pull this magnet out, then the solenoid will try to pull it back in to oppose the motion. So this will be south to pull it back in. So, and south, just as we worked out just now, is the right. Okay, so I have combined both already. This is for A and B together. So you can work out the other two yourselves. So actually this one should be here. Left and right should be here. For B, left and right. So you can work this out yourselves, right? Okay, now this one is a transformer question. Two identical bulbs with power rating of this are connected to an ideal transformer. So ideal transformer basically means that there is no loss of energy. It's 100% efficiency. So that means initial power in this, the primary, the input power is equals to the output power in the secondary circuit, right? So now we have 12 volts, each one is 12 volts and 20 watts. So we know the total power output already, just from this. The total power output here, each bulb is 20 watts. So the total power output, secondary power output is 40 watts. And on the primary circuit, since this is an ideal transformer, primary circuit will also be pushing 40 watts of power. Right? So what is the current in the primary coil? Now, we already have the voltage given to us here, 240V. So we can use the formula P is IV. We already know the power, input power is 40 watts. So I will be equals to P over V. So that will be 40 over 240. And this is 1 over 6. 1 over 6, which is 0.17 amperes. Now, what's the current in the secondary coil? So current in the secondary coil, we also have power, but now we don't have the voltage yet. We have to figure it out. So now these are connected in parallel, and the voltage across each is 12, which means if it's connected in parallel, then the voltage across all the roots will be the same here. So this here is also 12. The power source is also 12. So this is 12 volts. So we can use the same formula here. P is IV. I is P over V. But this time we use 40 over 12. And so the answer here is 3.33 amperes. So now if they don't give you the power directly, you can always use IV is equals to IV. Primary IV equals to secondary IV. That is simply using the concept of no power loss, 3.33 amperes. Okay, and then the number of turns of the secondary coil. So this one, when it involves the number of turns of coil, then we use the formula. Number of turns of primary to number of turns of secondary is voltage of primary across primary over voltage across secondary. It's directly proportional. So you follow PPSS. So now we want the secondary coil. So we can just put secondary up instead of primary. Just get the reciprocal, flip the whole equation. So over P, Vs over Vp. And so now Ns over primary coil, the number of turns of coil here is 1000. Connected to the power supply is 1000. Number of turns of coil. So here we have a value of 1000 turns. And so just substitute it here, divided by 1000 is equals to secondary voltage is 12, primary voltage is 240. So we just multiply in. So this is 12,000 divided by 240. And so the number of turns here will be 50 turns. And this is how you do it. Okay, guys, that's it I have for this video. All the best to you guys tomorrow. If you want to watch more revision videos, I'll leave the link in the description below. Again, you can click and watch that. Just do your best and don't worry about paper once it's done. Just focus on the next. All the best, guys.